In this first video on L'Hopital's rule, I'd simply like to introduce the rule as well as give some insight into why the rule works. I'll start off with a motivating example. We see here that we're looking for the limit as x approaches 1 of the function natural log of x divided by x minus 1. If I simply start by trying to plug in the limiting value of 1, you'll notice that in the numerator we get the natural log of 1, which is 0, and in the denominator we get x minus 1, which 1 minus 1 would give us 0 as well. If we were to end up with something like 5 over 5 or 100 over 100, we know that we would get 1. But that doesn't work when we get 0. So we get this situation where it's unclear how to quantify right away what we end up with. So thinking about trying to plug it in, we said we get 0 over 0. This is what we call an indeterminate form. So what we'd like to know is how are we going to solve a limit of this form? What I'd like to start with here is to move away from our specific example and think a little bit more generally to work with something like this. So suppose that I have two functions, f and g, and I'm going to assume that they're differentiable. But beyond that, I'm going to assume that f of a is equal to 0 and also g of a is equal to 0. And we're going to assume that we're trying to find the limit as x approaches a of the function f of x divided by g of x. Notice that this generalizes our earlier example where a was 1, f of x was natural log of x, and g of x was x minus 1. So note that this limit I've written here is exactly the same as taking the limit as x approaches a of the function now f of x minus f of a divided by g of x minus g of a. The reason that those are the same is that we've already established that both f of a and g of a are 0, so effectively I'm subtracting 0 from the numerator and from the denominator. The other thing to remember is that if I do the same thing to the numerator and the denominator, so multiply by the same expression, then that will likewise not change the limit. So I'd like to do that here in the following way. Let's multiply both the numerator and the denominator by 1 over x minus a. So do that to both of those. And what's going to happen is I can multiply that in there, but the other thing I want to do is use a limit property. So I have the limit of a quotient, and we can say that that's equal to the quotient of limits as long as those limits all exist. So that yields then the limit as x approaches a of f of x minus f of a divided by x minus a. And that whole thing divided now by the limit as x approaches a of g of x minus g of a, once again divided by x minus a. So now what we have here is equivalent to the limit we started with. And of course it looks like we simply made it more complicated, but the nice thing about this is hopefully these look a little bit familiar. The limit in the top is exactly how we define f prime of a, and the limit in the bottom is how we define g prime of a. So if that seems a little unclear that those are the derivatives, it could be because you're more familiar with another way that we defined the derivative at the point a. And so let's take a little pause here and think about this. So in terms of f prime of a, so we'll focus on f. We can define that as we did above, as the limit as x approaches a, of f of x minus f of a divided by x minus a. Or, what might be more familiar to you, is equivalently we can say that that's equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. So these are equivalents. They're both one way of expressing f prime of a. And to think about it, sometimes a visual representation can help. So let's consider some arbitrary f of x, or let's call it f of t. And I want to draw it twice. And what I'd like to illustrate on each of these graphs is one of these limits. So we're going to assume this is f of t. And likewise, whoops, maybe do that again. This is f of t. Okay, so these are our setups here. And in this left set of axes, let's focus on the limit of f of x minus f of a over x minus a. So what I want to identify is a, whoops, the point of interest. And let's look at some x over here. We can find f of a and f of x on the vertical axis there. And I can color in these 2 points. Then ignoring the limit, if you look at the quotient that we have there, that is the same thing as the slope of the line that connects these 2 points. We call that the line secant, line connecting these 2 points. That is what I've illustrated here. Now what happens is we take the limit, I can start to think about picking a point, now x, that's closer to a, right? So this is, let's call this x1. This is a new x. And considering this point, and now we would be looking at the slope of the line that connects these 2 points. And then I could do it again, right? Pick an x2. And I could continue this process until what's going to happen is the point x, as I move it closer to a, will eventually collapse onto a. And instead of having these secant lines, we would have what's known as the tangent. And the slope of that line would represent that limit, and that's what we're calling f prime of a there. So that's the line tangent to the graph of f of t at t equals a. But I'm going to argue that that's the same thing that we get with the limit on the right-hand expression here. So again, I have my same kind of general graph. Here, what we can look for is we're interested once again in the point a, and then another point that we're referring to as a plus h. Notice that this in structure is very similar. We have 2 points on our curve, and effectively what we're taking the limit of is the slope of the line secant to those 2 points. Then I can pick a smaller h value, right? We're sending h to 0. But as I do that, that once again brings me, it's called h1, closer to a. And I now have a different right point to look at, and consequently a slightly different slope. And we can once again pick another h value that's even closer to 0, called h2, and continue this process. This should look very similar to the process that we were doing on the left. And the same thing's going to happen as I send h to 0, then these 2 points are going to collapse onto a, and we're left with this tangent, so the line tangent to the graph at t equals a. And the slope of that line is again how we're defining f prime of a. So that's just a little recap on the visual behind this idea of a derivative at a point, and to see why that now is connected to the limit we got above. Now, to wrap this up, what we're left with is that's giving us a general idea of L'Hopital's rule. So I'd like to kind of formalize what the rule says. So one thing I want to point out is we focused on 0 over 0, but in fact, we can generalize this to cases in which the limit as x approaches a of f of x is equal to plus or minus infinity, and likewise the limit as x approaches a of g of x is equal to plus or minus infinity. Importantly, plus or minus infinity divided by plus or minus infinity is also an indeterminate form. So we've seen 0 over 0, but also plus or minus infinity over plus or minus infinity. We've got these two indeterminate forms. And what I'd like to finish with here is the statement of L'Hopital's rule. Okay, L'Hopital's rule, the assumptions we're making is that our two functions, f and g, are differentiable. And in terms of our limiting value a, we're going to let a be any real number or possibly plus or minus infinity. Now we've established these two kind of categories of indeterminate forms. So we're going to say here, if either the limit as x approaches a of f of x equals 0, which equals the limit as x approaches a of g of x, if that's true, or the limit as x approaches a of f of x is plus or minus infinity, and likewise the limit as x approaches a of g of x is plus or minus infinity. If either of these hold, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. That's going to be L'Hopital's rule. And I do want to point out one thing that maybe looks a little bit different from what we looked at above. You'll notice that I put this limit in there. And what that's allowing for is the possibility that when I take the derivative of f and g, I once again end up with an indeterminate form, in which case we're not done. But what that would say is that I can take the limit once again, and I would be able to use L'Hopital's rule again. So sometimes you can use L'Hopital's rule in succession a number of times, and you know you can stop when you no longer have an indeterminate form.